Okay, in this video I wanted to work through the quiz that I wanted you all to complete today in class. Just wanted to add a little bit of a commentary to each of these questions, and hopefully it clarifies the new polar coordinates components. Well, first off, on the top section, or in the top section of our quiz, I've reminded you of some important conversion rules. We can obtain an x and a y coordinate as long as we're provided an r and a theta coordinate using r cosine theta or r sine theta. And then similarly, we have an r squared as a result of the sum of x squared and y squared. It's our Pythagorean equation extension. And then tangent theta is the result of y divided by x. So again, we can compute r, we can compute theta as long as we're provided an x and a y. We can compute an x and a y as long as we're provided an r and a theta. So it's these rules that will allow us to convert between several different forms. Now in question number 1, we're told that we have a coordinate pair, so this coordinate is a combination of an x and a y. We have x and y, so that's why I chose to use these two equations here. R by itself would be the square root of x squared plus y squared. Now, since the square root sign wasn't really part of the equation to begin with, we have to be prepared for both positive and negative solutions, and after we work that out, we get positive or negative 2. For tangent inverse of 1 over root 3, because that's my y value divided by my x value, I don't know where 1 over root 3 is on the unit circle, so I can imagine that as the coordinates, 1/2 over root 3 over 2. That's going to be particularly helpful if this question is going to show up on a no calculator portion of the test. But even if you are allowed to use a calculator, we've got to be prepared to identify all solutions within a unit circle. Now the calculator will tell us that the tangent inverse of this fraction is 30 degrees, but we also should recognize that 210 degrees also produces the same ratio. Now we can't just blindly accept these answers. We do have to recognize why we're getting two different radii and two different angle measures here. If you're thinking about the position radical 3, 1 on a coordinate grid, well, that's to the right root 3 and up 1 in our rectangular world. That could be a polar coordinate with a radius of 2 pointing at the angle measure of 30 degrees. But if we point it to an angle of 210 degrees, we'd have to march backwards 2 units in order to land in that position. So we're not talking about the point that's over here. That's not what we're talking about at all. We're only talking about this position, but we can arrive there 2 different ways, 2, 30 or negative 2, 210. This particular question did not tell us to find all solutions or to identify multiple solutions, so either one would be acceptable. And as I'm scoring this, I would look at the work that you showed to get here. For question number 2, now this one does have a unique solution, because if we're thinking about a polar coordinate system, we're going to march forward 4 units at an angle of 2 pi over 3. Well, if you march forward 4 units from 2 pi over 3, that lands in this position right here, which has an x value of negative 2 and a y value of a positive 2 square root 3. That would be a good solution if you didn't have a calculator. However, if you were using a calculator, then the decimal equivalent would be accepted as well. When we switch to questions 3 and 4, I think we got a little bit lucky on these examples because they're pretty straightforward. We have a rectangular equation with x's and y's in number 3, and we have to turn it into a polar equation, something that contains r's and thetas. Well, again, from our summary notes, x squared and y squared is the same as an r squared, and x is the same as r cosine theta. So if we make that exchange, we have r squared equals negative 2 r cosine theta. And just to make things a little bit more manageable, we isolate the r value, because that's kind of like our dependent variable. So if r is our dependent, then that allows our theta to be the independent. And isolated here, we have r equals negative 2 cosine theta. So this shape here is a circle, and this equation here also produces the same circle. For number 4, same sort of question. We have r equals 6 times cosine theta. Now, I don't think this is written the exact same way as before, but if we're on our toes, we can see that multiplying both sides by cosine theta would get it to disappear or eliminate or factor from the right side and show up on the left. So now we have r times cosine theta on the left equals a number 6 on the right. R cosine theta is, of course, the same as x, so now we have the equation x equals 6. We know that x equals 6 produces a vertical line, so apparently r equals 6 divided by cosine theta does the same thing. When we look at question number 5, we're being asked to find two other forms of the polar coordinate 4, 2 pi over 3. So the same coordinate, I think. Oh, no, not quite. Yeah, it is the same. Sorry, I was looking at the wrong spot. The same coordinate that we had back here. What are some other ways to report that, not as a rectangular coordinate pair, but instead as another polar coordinate? So here again, the coordinate 4, 2 pi over 3 means to point in the 2 pi over 3 direction and march forward 4 steps. That's what lands us in this spot right here. Well, what are some other ways that we can get there? Well, if I had turned not to 2 pi over 3, but if I had turned to just, if I had over-rotated to this position, facing this direction and walk backwards, then I could land on this spot. That position is 5 pi over 3. So if we march backwards 4 units and face an angle of 5 pi over 3 radians, that's an alternate coordinate that means the same position. We could also think of the angle, keeping with the same idea here of marching backwards, think of this angle not as 5 pi over 3, but negative pi over 3, and that one works. If we do want to keep walking forward from our pole and use a positive 4 value, we can imagine this angle measure as negative 4 pi over 3. So if we had if we had rotated clockwise to this position, that's 4 pi over 3. Or if we wanted to, say, do an additional rotation. So not only do we rotate to 2 pi over 3, but we take an extra trip around the unit circle and land at that position as well. We can call that one 8 pi over 3. There are many other acceptable solutions here. Any one of these are fine. The instructions just said to find 2, so any 2 that you provide would be great. When you're showing your work for a question like this, I do like seeing diagrams, kind of like I've shown over here on the left, to help support your claim. Continuing on to the backside, looking for a polar equation that has the rectangular form of x equals negative 4. Well, x is the same as r cosine theta, so I'll make that exchange right away. And since we do prefer to have a dependent variable isolated from the independent variable, we'll divide the cosine to the right side, and we can call this negative 4 divided by cosine theta. If you wanted to, instead of using the division of cosine theta, we could treat that as the multiplication of secant theta, and that would be fine as well. The next question is almost identical, except y is r times sine theta equals 1. Divide both sides by sine theta, or rewrite it as cosecant. If we have r equals cosecant theta, that's also going to produce this same equation. For number 8, we had to try something a little bit more interesting this time. Again, we're trying to convert from rectangular form into polar form, so that means get rid of all of the x's and y's and replace them with r's and thetas. A helpful trick here is to go ahead and square this binomial y minus 4. That becomes y squared minus 8y plus 16. And then in the act of, just some algebraic manipulation, you might have noticed that subtracting 16 on both sides produces a result of 0. Then adding 8y to both sides puts us over here in this position. And then that presents some helpful exchanges for us. X squared plus y squared is the same as r squared. So now we're getting to polar form, and then y by itself is r sine theta. So we've now exchanged our rectangular variables for polar variables. We have r squared equals 8r sine theta. Divide both sides by r so that we can isolate our dependent variable, and we have r equals 8 sine theta. So there's no one set of methods to convert between rectangular and polar forms of equations. Sometimes it just takes a little bit of intuition, sometimes it takes some practice, or just guessing and checking, just kind of making an educated guess and seeing what comes out as a result. But make sure you show your work anytime that you do make those exchanges, and I'll be able to follow along if you label that um, on your quiz or on your homework. Now for this last example, everything up until now was done without a calculator, and 9 can be done for the most part without a calculator as well. It's just that some of these angle measures aren't super nice. Like for example, if I had a theta value of 15, normally that's a concern of mine. But if you notice here, cosine of 2 times 15 ends up being 30, and I could tell you what cosine of 30 is. That's the x value at 30 degrees, but I may not know the decimal. Other problems that seem fairly manageable at first can be a little bit challenging when you're doing these without a calculator. For example, if theta gets to be too large, like 345, and we go to double that, well then we're doing trigonometry outside of the unit circle. So what I wanted to show you here is that you can actually use the calculator as a shortcut to help fill in a table like this. And we didn't have time to introduce it yesterday, but that's okay. I wanted you to get a practice doing this by hand anyway. But if you do have a TI Inspire calculator, we can create a new document. And we're going to jump into the List and Spreadsheets page here. And like we've done in the past, I do want to create a label for my column headings. So I'm just going to put R in this first column, and I'm going to type the word theta in the second column. We might be able to insert the symbol for theta. I just think it's easier to type it. Now, what's interesting about R is you'll notice that in each of these cases, oh, sorry, I got that backwards. Hold on a minute. Okay, and I fixed that, and I didn't even realize it too, that when we typed the word theta, it turned into the symbol theta, so that's great. But what I wanted to point out here is that all of our theta values are increasing by a quantity of 15, so there's a deliberate pattern in this chart. If I'm not mistaken, this calculator will behave a lot like an Excel document where if you start a pattern, we'll go with 3 of these numbers here and click and highlight them. I think you can do this on the handhelds. But you click and highlight that, then you grab with your fill handle, we call it, down here in this bottom right hand corner. You can drag it down lower and fill in some values, continuing in that pattern. So I went too far. Let's see here. If I delete those, we can then stop at, oops, we can stop at 345. So we'll delete that, delete, and delete. So we've got all of those out of here. We go up to 345. Now, I wanted to show that to you because this becomes particularly helpful if we enter an equation up here in this row. And this is something we haven't used yet. We always skipped this row when we were working with this part of the calculator in prior units, but I want to show you something here. R is our dependent variable, and R is part of the equation that we're working with here. The equation is R equals 5 cosine 2 theta. So if I enter that equation into the calculator, it'll automatically use the theta values from this left-hand column to compute the results in the right. So I'm just going to start typing here. I'm going to put 5 times cosine 2 and theta, and I think we have the theta symbol in here. So there we go, and we can tap enter. Oops. Let's see what's going on. Oh, you know what? We might have to have some syntax at the beginning here. Let me clear this out. Let me try this again. There we go. I don't know what happened there, but this R colon equals wasn't displaying a minute ago. I think this will work better now. So 5 times cosine of 2 theta. Let's see if that's better. There we go. All right, so now we have all of our computed values down on the right-hand side. Since we have this available in our calculator, we can now copy them and put them into the table that's on our worksheet. Now, some of these answers are exact answers, and they don't display great, so I wonder what happens if we press Control-Enter. Nothing there. What if I press Control Enter here? Nope, nothing. So let me try one other thing. If I press the Home button and jump into the Settings menu, number 5, and adjust our document settings here. Right now the calculator will automatically display the results based on the input values. So if it can calculate an exact answer, it will. We want the approximate or decimal answer. So if I force the calculation mode to report as approximate and press OK, then return back to our current document. Yep, that worked. We now have the decimal value for that position. So if you have your decimal values here and you copy them into your table of data, then you ought to be able to regenerate this picture without too much effort. So I had to move some things around on the screen, but hopefully you can see what I'm doing. I'm looking at my calculator on the right, and I'm just filling that in on the left. And you could blindly copy all of these, and notice I'm only using 1 decimal point here, because in terms of graphing, that's about as accurate as we can get. You can blindly copy these, but I would also encourage you to be on the lookout for patterns that form. And I think I'm starting to see one now. So I've gotten to 105 degrees. And at 105, we've got a negative 4.3. At 120, we've got a negative 2.5, 0, 2.5, and then 4.3. So as I'm looking in this column here, I'm wondering if I'm seeing a pattern. The numbers themselves are repeating, and we're seeing some sign changes. So I wonder if going from 2.5 up to 4.3 would then give me a 5 here. And then maybe at 195, do we drop back down to 4.3? And then does this go to 2.5 and then 0 and negative 2.5 and so on? So that's kind of my guess right now. And if that's my guess, I can scroll through my calculator and see if that starts to match. So 4.3 at 165, do we get 5? Yep, that's a good match. Then 4.3 and then 2.5 and 0 and then negative 2.5. Yeah, so this pattern seems to be holding true. That might be some ways, or one way for us to save some time when we're filling out this table of data. Now the pattern won't be consistent for every single example that we go through, but there more often than not will be at least some pattern that we can use to fill out the remaining quantities or values in this table. Okay, and I did make a small mistake, but I've corrected that now. Okay, so I have a complete table, and I don't know why my scale got slid down out of the way here, but that's okay. We'll work with it. Now I have my table of data, and let's see, can I do this any better? Let's make it show up over here. Given the theta and r value, we now have a coordinate, r of 5 and theta of 0. We can now plot these points as needed. Okay, that took some rearranging, but I think I've got it now. All right, so if I'm facing a 0 degree, I can go to the 5 position on my pole. So there's my first coordinate that I'm going to place. At 15, I'm going to go down to 4.3, which is right about here. At 30, I'm going to place 2.5, then 0, then negative 2.5. Now this is kind of interesting. If I'm facing a 60-degree angle, so I'm facing in this direction, I would actually go backwards 2.5 units, and I'm going to label that position right here. Then same thing with 75. If I'm facing the 75-degree position, I go backwards 4.3 units, and I'll place my point here. Yep, 4.3. And then at 90, I go back 5 units, and I'll place my point here. Now, it's going to be helpful in order to keep track of the direction in which you've placed these points and start connecting those with smooth and continuous lines. Some students wait until the very end to connect them all, which is fine. It's just a little bit hard to see the path that you've just created. So I'm just going to pause right here, and I'm just going to imagine if I had started at this position and connected all of the points so far, this is what I have. Now you might be tempted to think that that's going to be a circle, but let's keep plotting some points and check this out. So I've gotten all of these. If I face 105, I go back 4.3. That's this position. If I face 120, I go back 2.5. That's this position. Oops, sorry, this position. Then 0. Ah, interesting. And now at 150, I've got a 2.5. So if I face 150, I'm at 2.5. Okay. And at 165, I'm back to 4.3. So these numbers are repeating themselves, which is pretty helpful. And I think we're starting to see a neat picture that's presenting itself. So if I continue to connect these dots, we're starting to see this this interesting shape here. And I'll just continue this as we continue to plot the points. All right, so the remaining points, oops, I forgot about these here at the very end. The remaining points do follow this nice pattern that we've established. Now, what I wanted to be real clear about is that plotting these points all at once is incredibly difficult to do, or it may be misleading. So imagine that I didn't have these lines drawn as I was plotting the points, and all you saw were these field of dots. Well, until you get real comfortable or familiar with these different shapes that we see in our let's see, that guy's missing. We want this one here, 2.5. So until you get real familiar with the trig shapes, it might be very difficult to sketch these graphs. So I've seen students try to tell me that this is the shape when they're all done, and that's just simply not correct. So again, pay close attention to the direction in which we created our sketches. In this case, we went down through here, came back out this outside, and then returned back to the center. And there's our final shape. Poorly drawn in this case, because I just didn't really take my time doing so. But I would ask that you be a little bit more careful than what I've done here and create a more appropriate shape. So now that I've fixed that point, if I come through and take my time a little bit more carefully sketching this, we'll see a shape that's a little bit better for us to work with. Now, each of these shapes do have names to them. I'm not an instructor that's worried about you learning the names in this class, but if you are interested in looking them up, I would encourage you to do so. If you look for polar equation names, I'm sure you'll come up with a site that describes the 4 or 5, maybe 6 different common shapes that we see when we graph polar equations. All right, so now all of the coordinates have been plotted. I believe they've been plotted correctly. The shape that we see on the right is a good representation of r equals, I think it was 5 cosine 2 theta. Hopefully this video helps with your work on this quiz. If you have any further questions, please let me know when we see each other in class next. Thanks for watching.